Good morning, ShmooCon. Happy Sunday. Everyone is awake, I can tell. Very, very energized. If there's anyone here who would like a small gift, who's awake enough to raise their hand? There you go, I saw you first. Enjoy. You can pretend that you're still at ShmooCon throughout the year. It's a sock puppet moose. Yeah, so really, again, hopefully everyone is somewhat awake. But a couple announcements for me before I pass it off here. First, thank you for wearing your mask. It's appreciated by all of us. We also couldn't run ShmooCon without everyone here, so we really appreciate your attendance and really want to hear your feedback. So please, if you have any feedback, feel free to email info@shmoocon.org. We're happy to hear about anything that you have, anything you saw, anything you'd like to suggest. We're open to everything. T-shirts and previous year swag will be available in registration, so after this talk, feel free to head over there. There's still a couple things left that you could purchase if you haven't had the opportunity. If you've lost anything this weekend, Lost and Found in Reg has found many things, so please also come by if you're looking for something. But with no further ado, let me introduce Dylan Franke, who's going to be giving us some cool information about how to look at Mac OS. So please, let's put our hands together and welcome Dylan.
All right. Well, thank you all so much for being here. Sunday morning, really appreciate you showing up so early after, I'm sure, a good Saturday night. Really excited today. This is my first ShmooCon. It's a pleasure to be here, and it's already becoming one of my favorite security conferences. So thanks to everyone that I've met. Everyone's been just so great, and it's been a lot of fun so far. Quickly, I'll just discuss who I am, give you a little background about myself. Currently, I am a proactive security consultant at Mandiant. We were just acquired by Google Cloud last year, so that's been kind of a whole process, but been really good overall. As well as just finished a job rotation with Mandiant's Flare Offensive Task Force. So this is a reverse engineering team. We do a lot of malware reverse engineering, as well as searching for ODAs and exploits used in the wild. And then also performing kind of some additional new security research. In my role as a proactive security consultant, I'm more focused on pen testing and red teaming. So my kind of main focuses are application security, source code reviews, and embedded device assessments. Before that, I have a bachelor's and master's degree in computer science, focus on computer and network security, as well as low-level systems engineering. And hobbies, enjoy playing guitar. I'm from San Francisco, so really enjoy cycling around the Bay Area. And, of course, hacking. So I'm excited to give this talk. I invite you to join me today as I dive into kind of my process that I've spent over about the last year off and on, looking for low-level vulnerabilities in Mac OS, specifically dealing with mock IPC mechanisms. This research is definitely still in progress, but I really hope there's a little bit of something for everyone in this talk. We're going to start kind of with a crash course on fuzzing and Mac OS, as well as the IPC mechanisms that it uses. And so really, if you're just getting into vulnerability research and fuzzing, I hope to really build up kind of that knowledge for you. Then we're going to jump into the memory corruption attack cycle that I've gone through in this research, and kind of just talk about some of the pitfalls that I've come across, some of the difficulties I've had, and hopefully inspire you to look at some interesting new attack vectors and fuzz them. I'm then going to talk about some of my next steps that I'm excited about in this research, and then we're going to have some Q&A. So without further ado, let's go ahead and jump into a bit of background knowledge here. So just as a very basic definition, let's talk about what fuzzing is. My definition of fuzzing I like to use is sending unexpected inputs to a system in the hopes of making something unexpected happen. So pretty simple, where a lot of times this just looks like random data. When we get more sophisticated, we start looking at grammars and building more kind of complex messages to send to a system. But at its core, this is what fuzzing is. What is an attack vector? So an attack vector is the channel in which we send an input to a system. Therefore, it's the way in which we fuzz, the communication channel to fuzz. And a couple examples attack vectors, you can really get creative with this. The world is really your oyster, and I urge you to do this when you're thinking about what is actually attackable. So if we just think of a laptop, for example, there's so many different ways to attack it. We can look at Bluetooth connections and how incoming data is parsed, maybe from devices connecting to it. We can look at inter-process communications like we're going to be doing today. We can even look at like push notifications coming in to a mobile phone maybe, peripherals that are connected, maybe a device driver that they use, and of course wireless connections. There's really an endless amount of ways that you can attack a system. So just as a couple of examples of attack vectors, I just have a couple examples here. For example, if you're looking at Adobe Acrobat, PDF preview and viewing and editing application, the attack vector here might be opening PDF functionality. So an input then might be a maliciously crafted PDF. But we don't always just need to have an attack vector that's opening something with a program. I think in fuzzing a lot, we think of just opening AFL, attaching it to a program, and sending a bunch of inputs to it. But we can really fuzz anything. We can fuzz parameters in a web application like you see here. We can even fuzz, like I mentioned, Bluetooth data incoming to a smartwatch. So really the bottom line here I'm saying is get creative with this. And I tried to think out of the box when thinking about what I wanted to fuzz. So why do we even want to perform fuzzing, you might ask? And that's because pretty much everything is built on top of memory unsafe languages, aka C and C++, and we want to try to send inputs that cause that C program to crash. And depending on the crash that we're able to trigger, we might be able to exploit a buffer overflow, a heap overflow, a use after free, a double free, or a memory leak, which could give us information that we can use to bypass ASLR. So here's just an example, kind of tying all these concepts that we've discussed together. This is an Adobe Acrobat use after free vulnerability. It resulted in an RCE, remote code execution. The attack vector here, as you can see, is opening a malicious file, so that maliciously crafted PDF. And if we look at the description, there's an existence of an object prior to performing operations on the object. It's not validated. So this is a classic use after free vulnerability, and this was discovered via fuzzing. So there's a lot of really interesting research that fuzzing can produce, and often we catch very critical vulnerabilities in high-profile software like this. So there's two main types of fuzzing that we're going to be discussing today. The first is mutation-based fuzzing. So this is when we have a bunch of existing inputs, and these might be inputs that we've seen in the wild. They might be known good inputs. They might be like a bunch of valid PDFs that we want to send to Adobe Acrobat, for example. And mutation-based fuzzing is modifying those known good inputs and then sending them to the program and seeing what happens. On the other hand, we have grammar-based fuzzing, which is going to be generating inputs based on some sort of syntax or rules that we use to define the structure of a valid input. So an example of this, maybe you're fuzzing a browser and you want to try to generate interesting JavaScript payloads. You might write a grammar for what is valid JavaScript syntax and then generate a bunch of different JavaScript functions and objects based on that grammar. Today, though, kind of based on the research that I did, we're going to be looking at mutation-based fuzzing. So taking those existing inputs and then modifying them and seeing what happens. Okay, so we've established what fuzzing is. We're going to jump in now a little bit to a little Mac OS background. So at a basic level, what is the XNU kernel? So this is the kernel that powers Mac OS. Stands for X is not Unix, which is kind of funny. There are three main components of it. So there's the mock layer, which is responsible for a lot of low-level tasks. So this will be things like thread management, inter-process communication, and memory management. You have the BSD layer, which is going to be a bit higher level. That's going to be more file system network-related tasks. And then you also have IOKit in the XNU kernel, which is a framework that developers can use to create drivers. Today, we're going to be really focusing on this mock layer. So we're kind of targeting the lowest layer in the macOS kernel, and specifically looking at inter-process communications. So inter-process communications, why do we need them? Because processes need to talk to each other. They need to talk to each other for a lot of different reasons. Sometimes this is thread scheduling. Sometimes this is alerting another process that it's finished with a task. Sometimes it's used for remote procedure calls. There's a lot of different reasons why processes need to talk to each other, but they do. And there's a lot of ways they can do it. So on macOS, I've listed a few here. Mock messages are going to be really what we're looking at, and these are the lowest level IPC mechanism that exists on macOS, and they're actually the basis for many of these higher level mechanisms that you see here. So they're kind of the building blocks. So by targeting that lower level mechanism, my hope was that we could cover kind of all of our bases here on these other IPC mechanisms. Okay, so looking a little bit more into mock IPC and how it works. First, let's define what a mock port is. It's pretty simple. A mock port is just an IPC message queue, and it's managed by the kernel. So you can really think of this as just kind of a letterbox that's processing incoming messages, and then there's messages being sent to it, and then there's messages being dequeued or read from it. With mock ports, there's this notion of a port write. So this is a handle to a port that allows some operation on that mock port. So typically this is either the ability to send messages to the mock port or receive from the mock port. So here's the most three common port writes that you'll see. A receive write allows you to receive a mock port's message. A send write allows you to send messages to that mock port. And send once, which allows you to send just a single message to a mock port. Then you lose that write. And you can actually, if you have a macOS operating system, you can use the LSMP tool that you see here to view information about mock ports. So here we've done that with the KEXD process. And as you can see, there's a ton of different mock ports that are being utilized by it. We see mostly send mock ports with a send write, and we do see a few with a receive write, which is pretty typical. Okay, let's talk about how we establish a connection via mock IPC to get these processes talking together. So there's this notion of a bootstrap server, and this is actually stood up by launchd, if you're familiar with macOS. It's one of the first processes that gets launched on Mac, and it essentially sets up this bootstrap server, which will help establish connections with other mock ports. By default, any process can send. They have a send write via mock to this bootstrap server. And because of that send write, the bootstrap server can help broker and negotiate communications with other processes. I'm also going to define here what a mock service is. So this is just a mock port like we defined before, but it has a specific name that is registered with the bootstrap server. So the bootstrap server, let's take the example com apple moose here. If we have that service, the bootstrap server will have a mapping of that to a specific mock port, and when someone looks up the name com apple moose, the bootstrap server will be able to say, all right, here is that mock port, and here's the specific send write to that service. So here's just a quick example of how we would communicate with the service. Let's say Alice allocates a new mock port with a receive write. Then she's going to use the bootstrap server. She's going to register com apple moose with the bootstrap server. And by doing that, she's giving the bootstrap server a send write to that port that she allocated. And she has a receive write to it. Then let's say Bob asks the bootstrap server for the service com apple moose. And the bootstrap server is going to say, all right, I will give you a copy of the send write for Alice's mock port. Now that Bob has that, he can use that send write to send mock messages to Alice's mock port. Okay, so now we know how the connection gets set up. What do these mock messages actually look like? So a mock message is a struct that's used to exchange data between mock ports. And you see a bit of a diagram here. We won't dive too much into this. The main things kind of to point out here is the message size, which is in the mock message header, the remote port, which is going to be the mock port that we are sending to, and then the message body here, which is going to be typically binary data that the receiving process knows how to interpret. So there's not a lot of specification of what can or can't be sent in this body. There's actually no limit to the amount of data that you can send in the body either. It's really for the receiving process to kind of define and to expect from the sending process. So messages are sent and received via the mock_message function, API on macOS. And so this is used for sending and receiving messages. The option here, the second field, will specify whether we're sending or receiving a mock message. And then this mock message header T type is our message header, which we see on the right here. So this is going to contain all of the information, including the message body. Okay, perfect. So we have gone ahead and defined what fuzzing is. We've defined a little bit about macOS and how IPC mechanisms work within it. I'm now going to talk through my process for attacking IPC mechanisms on macOS. The cycle that I went through here was first identifying an attack vector, which we've done a little bit by identifying we want to fuzz mock IPC, but can we limit the attack vectors that we're looking at, and specifically the processes that we're targeting. Then we're going to look at how do we generate a corpus of inputs. So a corpus, as we'll talk about in just a minute, is just a grouping of valid inputs that we've seen and that we know is going to be processed in some way by the receiving process. Then I'm going to talk a little bit about how I wrote a custom fuzzing harness to send mock messages to processes I was interested in fuzzing. Then I'm going to talk about the actual fuzzing process and producing crashes, as well as generating code coverage. And then finally, I'm going to talk about how do we identify what is a relevant or meaningful crash. Then we're going to get into kind of next steps and questions. Okay, so let's talk about how we can abuse mock messages. The first major way, and this is not new research here, this has been done for many years, but mock messages can be abused to create a sandbox escape scenario. So let's say you have found remote code execution in Safari, a web browser. That process is going to be sandboxed nowadays. That wasn't always the case, but now that remote code execution on Safari is not super meaningful because you're still within the sandbox. You can't access the user's files, you can't install persistence mechanisms, you can't do anything really. So mock IPC exists as a channel here because from that web browser process, we might be able to send mock IPC messages to a message handler that's outside of the sandbox. And by doing that, if we can corrupt the message handler and the underlying process, we have effectively escaped the sandbox and turned what was a pretty mundane Safari RCE into a full system takeover. The other way that mock messages can be abused is for privilege escalation. So let's say you have an unprivileged process running just as the local user. You can perform the same sort of attack by targeting the message handler and take over a privileged process. So these are kind of the two ways mock messages have been abused in the past. I wanted to focus on looking at sandbox escapes to kind of hone in on my attack surface a little bit. And so to do that, I used a tool that's publicly available by Jonathan Levin. If you know anything about macOS research, he's very knowledgeable in the space, and I've read a lot of his material. He's got some great tools as well. One of these is SB tool, and this tool uses macOS's built-in sandbox check function, and what you can do is essentially attach it to a process and say, I want you to check what I'm able to do from this process. So here we're attaching to this process 2813. This was Firefox. and I'm saying, which processes or services can I send mock messages to? And it'll actually go through and generate a list of services I can interact with. So this helps a lot because we go from honing in our attack surface. We're looking first at all macOS processes that receive a mock message, which is pretty much every process on macOS. Then we're just looking at processes with a mock service, but by using this SB tool, we're able to look at processes with a sandbox allowed mock service, and that really helps us hone in that attack surface. Just want to point out a couple of previous researches that have gone on kind of in this same vein of mock privilege escalation and sandbox escapes. One, I had the privilege of seeing a couple years ago at Black Hat about using mock messages and IPC mechanisms to break out of Chrome. And then some work that's been really inspirational and helpful to me was I believe a 6-part series blog by Ret2 Systems, which talks about their Pwn2Own 2018 exploit, where they found first RC in Safari and then a sandbox escape via mock IPC messages, and we're able to get full RC on the system. So highly recommend reading this blog post if you're interested about anything in this talk. Okay, so we're identifying an attack vector. We've kind of slimmed down the number of mock services that we're looking at. Now we need to find an entry point, which is a way that we can send our inputs through that attack vector into the system. So we know that the mock message function is used to send mock messages from one process to another. So kind of my first idea here was, why don't we just go ahead and hook onto a process, and then whenever it goes to send a mock message, we'll just do some dumb bit flipping on the message body and see what happens. So that's exactly what I did here. You can see the mock message function is sending by land. That's going to be processed by the kernel, sent to the message handler, and then the receiving process is going to say, okay, that sending process said by land. Now here, what I started doing was hook with LLDB, the mock message call, and then mutate that message body to by C, and then the receiving process is now going to get that message and process it accordingly. So the pros to this approach, it was simple, and it was pretty similar to what we're going to expect in maybe our end exploit, because we are probably going to need to use the native mock message send function call. But it was very slow. I was at the mercy of whatever application I was hooked into to send messages, and sometimes messages don't get sent for a while. So as far as being efficient at fuzzing, this was a really bad approach. There were also a lot of points of potential failure along the way. You know, we're getting it processed by the kernel, we're using LLDB. There were a lot of ways it could fail. And then probably the biggest problem here was we were dealing with 2 different process spaces. So one was the sending process, which was actually calling mock message. The other was the receiving process. And getting code coverage, which I'll talk about in just a minute, proved to be pretty difficult in that specific scenario. And then it was difficult to determine which message actually caused a crash, kind of because of that 2 different process spaces. So I went ahead and decided to shift gears a little bit. I thought, okay, instead of waiting for mock message send to be called, what if we just write a program to call it ourselves? Then we don't have to be at the mercy of the sending process. So I did that. I wrote a program that would just loop and continue to call mock message. And then I thought, okay, what if we actually go a little bit further? We're still having our messages processed by the kernel. What if we actually just called the message handler directly? And I like to refer this as getting close to the system of interest. So we're getting really as close as possible as we can to that message handler and saying, here's our input. The pros of this is it becomes much, much faster than we saw before. It's also in the same process space now, which makes it a lot easier for instrumentation and code coverage. And then it's much easier to know which input caused a crash and then replicate it. There are a couple cons here. One would be it's a bit different from the end exploit. We're not actually going to be able to directly call this message handler from Safari, for example, because it's not an external API that's exposed. We also might need to invoke initialization routines on that receiving process before we can just call its message handler. But this approach proved to be much more useful for me. Okay, so we've talked a little bit about identifying that attack vector and how we might actually want to send inputs to it. Now let's talk about generating a corpus of inputs. So we have that attack vector. Now what do we send to it? In fuzzing, sending totally random data, it really depends on what you're fuzzing, but in the case of mock messages, sending random data is not likely to produce meaningful crashes. And that's because there's a lot of exceptions that are handled and input validation that occurs in mock IPC. So we're probably not going to be successful just by piping dev view random into it. We need to identify examples of valid mock messages first, or build a corpus. Before I talk about this, I just want to mention a couple things. When you start debugging on macOS, which you're going to need to do to generate this corpus in fuzz, I would highly recommend setting up a virtual machine, because when you start attaching to processes with LLDB, you're going to need to disable system integrity protection. You're probably also going to want to disable the built-in report crash daemon, as well as some of the native sleep functions that are enforced by default. And there's a really good DEF CON talk from a couple of years ago that I linked here, which provides kind of everything you might want to think about if you're fuzzing on macOS. Okay, so let's get back to generating that corpus of inputs. First, we want to find a mock service of interest. So in our case, one of the processes that I saw accessible from sandboxes most commonly was the core audio daemon. This is COM Apple Audio Core Audio D. It handles all interactions with audio hardware. It also performs a lot of privileged operations, and as I mentioned, it accepts mock messages from a lot of different processes. So one of the things I did was I attached to Core Audio D, which was the binary which the Core Audio service launches upon startup, and saw that it loaded the Core Audio framework, which you can see in this first image here. And so I was like, okay, I'll pop that into IDA Pro. We'll start looking at actually how these messages are handled. If you try to do that, though, you see that the Core Audio framework binary does not exist on the file system. And this kind of threw me for a loop for a little bit until I figured out that starting with macOS Big Sur, most framework binaries are actually not stored on disk. They are stored in what's called the DILD shared cache, which is a way that the macOS optimizes using these framework binaries, but they're not just sitting on disk. Thankfully, there is some useful tools to extract binaries from the DILD shared cache. I've linked to one here, and we can actually fully recover those with a lot of symbols still intact. So this was very helpful. So now I had the Core Audio Framework binary, and I could start performing some static analysis on it. Okay, the next thing was finding the function which handled the mock receive functionality. And you might have been wondering, didn't I say in the beginning that the mock message function was used for sending and receiving? This is true, and initially I thought I could just hook onto this function and see all the messages incoming. But actually this, when you're receiving a message, in order for kind of non-blocking I/O to occur, it traps to the kernel. And so if you want to use mock message to look at received functions, you actually need to kernel debug or write a kernel extension. And so I looked into this a little bit. It's a bit annoying though, because you have to use 2 machines on macOS to kernel debug. And you're also seeing every single mock message that's sent on the system, and it's tough to isolate the target process that you want to look at. So I was wondering, is there an easier way that we can actually figure out the function that's receiving mock messages. And it turns out there is in a lot of cases. So Apple provides this thing called the mock interface generator, otherwise known as MIG. It's an interface definition language compiler, which means that it abstracts a lot of the mock IPC layer away and allows you to create stubs, which you can call, and then it handles kind of all the mock IPC under the hood for you, which is nice. So this diagram shows a little bit about how this works. You specify a definitions file, and then you're able to define stubs and how they should be handled. It's very high level. And then the MIG compiler will take care of all the mock IPC stuff under the hood. So I thought, okay, this is cool. What if I just look for these MIG subsystems and then try to hook onto them? This is actually what the RET2IO team did in their research that I mentioned at Pwn to Own. There's a pretty useful Hopper script that I kind of converted to IDA Pro in order to detect MIG subsystems within a binary. But you can also just look at symbols and kind of look for subsystem in most binaries in MIG, and you'll pretty quickly determine where the MIG subsystem is. So once we do that, here's an example of one of the subsystems I spent a lot of time fuzzing, and hopefully you can see this screenshot okay. But at the top of the function you see here, this is the HAL's MIG server subsystem. We have two inputs to the function, and they're both mock message header T's types. So that first input, which is going to be the RDI register, is our incoming mock message. And then that second input is actually the one that's going to be returned to the sending process. So this process handles incoming ones, and then it sends a response back to the sending process. Okay, so that incoming mock message is then going to be parsed. And you can see here that the server is parsing out the message ID that's being sent, which is one of the fields you can send in a mock message. Then it's getting the offset to the MIG server subsystem that we looked at the slide before. And then it's indexing into that. So it's a function lookup table based on the message ID. And then it's calling the desired function. So this is pretty typical RPC-like functionality. We're parsing a message ID, getting a function from that, and then calling it. And you can see here are the RPC functions that were actually exposed by Core Audio via this MIG server subsystem. So quite a few. They all start with _X, which makes it easy to identify them. And here's an example of opening the Core Audio system. Okay, so now we know actually what function is receiving messages for a process that we're really interested in. And so I wrote a simple script here to just hook on to that message handler that we found using LLDB, and then just start spinning out that RDI register, because that's going to contain our mock messages. So this is just a quick video. Hopefully you can see it okay. We're just looking first for the Core Audio daemon process so that we can attach to it with LLDB. Then we're using this mock message dumper script to specify the process ID, then the library or the module that we care about, the Core Audio framework, and then the function, which is that HAL MIG server that we talked about. And then we should start seeing messages being dumped and saved to the system. And I would commonly open up like YouTube or a music player so that I could generate more traffic by interacting with audio devices. You can see when we opened up Apple Music there, we started getting a lot more messages. And so people will write custom scripts to generate traffic on a system in order to see more messages. So this is a pretty common technique. But doing this, we were able to save a lot of valid mock messages that we could then use to fuzz. Okay, so we generated a bunch of valid inputs. Now we need to figure out, or we need to write code to actually send that to the message handler. And to do this, we use what's called a fuzzing harness. So this is code that you write that allows you to send input through an attack vector. Or at its core, it's just calling a desired function. So this is often pretty simple to do on Windows. I'm sure a lot of you have used load library and get proc address. On Mac OS, it's pretty similar. There's the DL open API, which you can use to load a specific dilib. And then there's the DL sim function, which you can use to get a specific offset for a symbol within that library. But the specific method that we care about, this MIG server function, was not actually externally accessible or exported. So I ended up having to write my own Mako symbol parser, go through the whole symbol table, figure out the specific offset, and then call that offset directly. So that's a little bit of a talk for another time. I'm hoping to open source that process after this talk. Still going through some approval processes at Google, but was pretty interesting to work through for me. So here's how this works. This is the harness. We're specifying here the core audio framework as our library. We're specifying the function that we want to attack, our attack vector, the MIG server. And then we're passing in, this attackf flag is passing in a specific input that we want to send to the message handler. And you can see here, the first output there is the mock message that we're sending. We call the function, we actually get an error, and then we get a returned mock message from the receiving process. So we've built a harness, so now we can send messages to the function we care about. Once we have that, we can then use a fuzzer. And a fuzzer is just a program that generates inputs that will be sent to a system and monitors for crashes. So with this fuzzing harness, what does this actually look like? Well, step one is going to be taking in our inputs, which we have generated in our corpus. We're going to pass those to the fuzzer. The fuzzer is going to start mutating those inputs. It often does so randomly, but there can also be kind of additional steps you can take to do so more intelligently. It's then going to send the message through our fuzzing harness directly to the message handler. And then the fuzzer is going to look at, okay, was there a crash that occurred in that receiving process or no crash? If it's a crash, it's going to save the input because that's a good input that we care about. If not, it's going to continue to modify that message and maybe move to a next input. So you can do this for as long as you want, and you generally have to do it for a long time to generate interesting crashes, in mature code at least. So let's take a look at this toy example here, though. The process that I just showed you here of just randomly flipping bits might not be super useful in a function like this. If you look at what's going on here, we're processing an incoming string, and we're first looking, is it greater than 3 in length? We're then looking, okay, is it equal to length 3? And then we're looking, is the first character S? And then finally we're looking at, is the string secret? If so, we dereference a null pointer and we crash. This process that we just talked about is going to have a really hard time of finding that crash because there's so many different conditions and we have no insight other than the program crashed or it didn't. And for this reason, we need what's called code coverage. And code coverage is tracing a program's execution flow in order to identify new code paths. So what this means is that instead of just looking at was there a crash or was there not a crash, we also are looking at did we go down a code path that we've been down before, or did we actually just find a new code path? And if we found a new code path, that's actually a really interesting input for us, and we want to save that back to our corpus and start fuzzing with it. So this is a very commonly used technique in fuzzing, and it'll increase your success rate by a very large margin, just because you're able to see actually what's going on in the receiving binary. So how do we determine code coverage? First, on the right, this is actually one of the targets that I was fuzzing, and you can see the code coverage for this specific function. The green nodes are code paths that we've hit, and the white nodes are code paths that actually haven't been explored yet. So you can get a pretty good idea just by looking at this what you still need to fuzz. And you can look at sort of these branch conditions and see, why am I actually not getting to this part of the code? And this can really help you increase the efficiency of your fuzzing and know that you've kind of covered all code paths. So for actually getting code coverage, how do we do this? If you're fuzzing something with source code, it's pretty easy. You can use AFL++, libfuzzer, or gcov, and actually add in these libraries directly into the source code to output that coverage information. But it becomes quite a bit more difficult when you're doing black box fuzzing, which is what we're doing here. So we don't have the source code for these Apple system binaries. And so to get that code coverage, we actually need to use dynamic instrumentation. So this is using either Frida, which is a very common dynamic instrumentation framework, or in my case, I decided to use something that my colleague at Google wrote called tinyinst. But what both of these programs do is they essentially attach to the receiving process, and they just look at the execution flow and print out sort of where we're at in the process. And it'll then be able to tell you if you're reaching a new area of the process that you haven't seen before. Then once you have that code coverage information, you'll load that into a analysis program, which the one you see here is a really commonly used one for IDA Pro and Binary Ninja. It's called Lighthouse, and it works really well. It'll highlight exactly where you've been and where you need to go. Okay, so next, I got into actually fuzzing our end service. There's been a lot of build up to getting here, and I was pretty excited to get started. The fuzzer that I used here, you can use whatever fuzzer you like. I used the Jackalope fuzzer, which once again is written by Yvonne Fratrick, one of my Google colleagues. And I decided to use this just because I really like the options it exposed. And it was simple for me to use. I could also ping him if I had any questions, which was the biggest reason. One thing that you can do and that you definitely should do is enable Apple's guard malloc, which is very similar to address sanitizer on Linux. It places restricted pages around all memory allocations so that if there's maybe a memory access off by 1, you'll see those very granular memory accesses that might be disallowed and lead to something like a buffer overflow. Then I used tinyinst, as I mentioned before, to perform dynamic instrumentation and dump that code coverage information, and then Lighthouse to interpret the code coverage. And here is a little bit of a screenshot of just running our fuzzing setup. So at the top, you see a whole bunch of garbage that's being passed into this command. Basically, we're just specifying our fuzzer, Jackalope, specifying our corpus of inputs, telling it that we want to use the custom fuzzing harness that we wrote, and then specifying that the module that we want to instrument to get code coverage. This first sort of highlighted red area is just showing that guard malloc has been loaded into this process. So all allocations are going to be placed on a 16-byte boundary here. That's great. And then actually in this screenshot, we see a crash that occurs. This was just a C++ exception, so it wasn't anything super interesting because it was handled by the receiving process. But we do see that when that occurs, there's instrumentation that is produced by tinyinst, and we can see exactly where that happened and how we got there. Okay, so once you start fuzzing, I mentioned before, you want to regularly check your code coverage because we can learn a lot about where the fuzzer is and isn't getting to. And a great goal to have in fuzzing is just to cover as much of the binary as possible. So hit as many code paths as you can. If you've covered all code paths and you haven't produced a crash, you can be pretty confident that it is looking quite nice. And this is why open source fuzzing projects like Google OSS Fuzz are commonly outputting the amount of code coverage that they've achieved and trying to always up that number. Okay, and the final step here is going to be identifying relevant crashes that you're able to produce while fuzzing. Not all crashes are created equal, and some are likely not exploitable based on basic heuristics you can look at. So ones that you really care about, a crash on write, a crash on execution, an illegal instruction crash, corrupting the heap, or a stack trace that contains like a memory allocation or free function. Things that you might not care as much about, a crash on read, although this can be used to leak memory, which can be useful in building exploit chains. A handled exception, a null pointer dereference, or a stack recursion error. There's some useful tools that you can use to apply to the crashes you're generating and triage them. Apple provides a tool called Crash Wrangler, which is a bit outdated, but it does still work well to kind of look at some of these heuristics and tell you if you should worry about a specific crash. There's also a good project on GitHub called CrashMon, which uses LLDB to do the same thing. So highly recommend using those tools to speed up this process. One really important thing when looking at crashes is whether you're able to reproduce that crash. Oftentimes, you'll hit a very specific use case, and you won't be able to reproduce a crash, which is very frustrating. But some of that is a very important thing that you need to keep in mind. So you should be able to run that input through your fuzzing harness again and continually generate that crash in order to have what will likely be a reliable exploit in the end. Okay, so a couple takeaways and just talking about what we've covered. Really hope this crash course on fuzzing and mock IPC mechanisms was useful for all of you. We went through quite a bit of material talking about the attack process and things you might want to think about as you do some of this fuzzing research yourself. Identifying an attack vector, generating a corpus of fuzzing inputs of known messages we can send, writing a custom fuzzing harness, actually fuzzing, producing crashes, looking at code coverage, and then triaging those crashes. Hopefully you also saw some of the mistakes that I made. That is something I really want to underline here, that it was not always easy or that I knew what to do next. And this is just a common thing in vulnerability research. But it's also a lot of fun because you learn a lot in the process and you're constantly getting better. And I really hope I've inspired you to do some vulnerability research as well. As far as next steps for this research, I want to continue increasing the code coverage of these mock IPC handlers that I've been fuzzing. One of the things that I've started to implement is stateful mock message fuzzing. So it turns out the message handlers sometimes care about the order in which mock messages are received. And so I've started looking at how do we determine the order in which to send messages to increase our code coverage. So that's some research that's still going on. Additionally, I mentioned when you're calling a message handler directly, sometimes there are initialization routines that need to be called before you can actually send a message. And so I'm working on automatic initialization of some of these mock service binaries. I mentioned I'm going to open source my mock message dumper and fuzzing harness. I apologize I wasn't able to get that approved by this talk, but it should be hopefully very soon. And you can follow me on Twitter or check out my blog. I'll be sure to update you when I release that. And then additionally, I would love to collaborate with any of you that are interested in this sort of research. Always looking for people to ping ideas on, talk about kind of new techniques or methods that you all have, and hopefully collaborate on research. So with that, thank you so much for listening, and happy to answer any questions you have. Yes, I did. Yep, I did do all the fuzzing within a VM. I used VMware. You can definitely use VirtualBox. I know people who have also fuzzed macOS with QEMU, although it's a bit of a pain to get set up, and there's some licensing issues with doing that. So VMware was a good process for me. You do need to run VMware on a Mac, which is something to be aware of if you want to go that route.
Did you do that on like a hardware?
That was actually just on this laptop. Yeah. And then also had a couple of other Mac OS laptops that I was just running kind of overnight all the time. Yeah, you can definitely do this in the cloud too. It's pretty expensive, which is why I didn't go that route. But yeah, AWS, you can definitely start up a cloud server and run these types of things. Perfect. All right, I think we're at time. Thank you all again so much. That's a great question. I honestly haven't looked into that implementation a whole lot. I know you can enable that on iOS. It's supposed to like. Okay. Interesting. I haven't explored that at all. That would be really interesting. I would assume there would be a lot of long services that would be disabled when you do that, and it would probably severely limit the attack.
Test.
But I
Keep going.
That's a really interesting place to do research.
Oh, yeah.
Test. Test.
Yeah, that was really good.
Window washer. You good? Okay.
It erased your name. Look at that. Anyways. Cool. Good morning, ShmooCon. Happy Sunday. Woo! Little bit energy. People are waking up here. Maybe you got some caffeine in them. That's good. It's good. Couple announcements from me. First, we appreciate any and all feedback that you have here at ShmooCon, and if you'd like to submit that, you can send it via email to info@shmoocon.org. So any ideas you have, suggestions, we're open to everything. So please feel free to send that along. We have t-shirts and previous year swag available for sale, still in the registration room. So after this talk, feel free to head out there and check that out. If you're interested in purchasing a set of the videos, you can also do that at a table out here for cash. You can check in with Ted, who has his table set up if you'd want the videos more quickly. Outside of that, really what I'd like you to do is put your hands together and help me welcome Joel to the stage, and he's going to really tell us some interesting things about scanning the internet. So, welcome, Joel.
Thank you. All right, welcome everyone to the dangers of building a recursive internet scanner. If you're wondering what's happening over here, this is a bbot scan, and this is basically a visualization of the scan in real time, where each one of these little nodes is like an IP address or a host name. Basically, this specific scan right here is a scan against nasa.gov, which is a pretty big domain. Throughout the talk, there'll be a lot more of these fun little visualizations. Who all here has used bbot, just out of curiosity? Okay, we got a couple. Okay. Intended audiences for this talk, mainly like developers and pen testers, bug bounty hunters, anybody interested in OSINT. But don't worry if you're not on this list. It's totally fine. Basically, when it comes to writing a recursive internet scanner, it's actually kind of dangerous. So if you can think of like writing a recursive scanner as launching rockets into space, this talk is basically going to be like a blooper reel of all the rockets exploding. Even if you're not a hacker, you'll probably enjoy it just for the entertainment value. Already introduced me. I work at Black Lantern Security. I've written a couple other tools, including Trevor Spray, but I'm the main author of bbot, and also an ex-Spiderfoot dev, which I'll get into in a minute. So what is bbot? bbot stands for Big Huge BLS OSINT Tool, kind of a mouthful, but it's actually a lot more than just an OSINT tool. It's the recursive internet scanner that this talk is about. But in order to sort of understand like exactly what a recursive internet scanner is, it's important first to understand Spiderfoot, because bbot was inspired by Spiderfoot. So this is where Spiderfoot comes in. Okay, so I want to tell you a quick story about how I fell in love with Spiderfoot. And just hang with me here for a few minutes till we get into the explosions. So rewind to 2020. We at Black Lantern had just started doing regular assessments for a Fortune 500 client. This client's business strategy was to acquire other companies. So whenever they had an acquisition, they would basically hire us to hack their new subsidiary and just see how secure they were. So we did a lot of these assessments where basically the first half of the assessment was external. We'd get to do like OSINT, sort of like phishing, hacking web apps, that kind of thing. And then for the second half, they'd send us on site and we'd do an internal pen test. And this was actually really insightful because it basically allowed us to see the external side of a company, and then immediately after that, the internal side, and sort of see what was exposed and what wasn't, and like how they compared. But then we started to actually discover something really concerning, which was that there's this pattern where we would, once we got on site and we started doing internal stuff, we would scan for a lot of the same vulnerabilities and stuff that we would scan on the outside. And obviously, we'd find a lot more of them, because internal networks are typically bigger than external ones. But what was concerning was that we would find things that were vulnerable, and then when we exploited them, we would find out that they were actually exposed to the internet. But then, like, why didn't we find them in the external portion? So we were like, okay, how did we miss this? And it turns out that we had scanned for that vulnerability externally, but we hadn't found it because we just didn't know about the subdomain. So it's kind of hard to hack a website if you don't know it exists. So that's what we found out. So basically, this exposed some flaws in our OSINT process. We realized that we weren't finding everything. That there was a lot, sort of like an iceberg of stuff that we could have found that we weren't able to. So if I was to like sketch out the process that we were using for our OSINT, this is basically it. This is like typical stuff, right? You have your targets, you do subdomain enumeration with like a mass, and then once you have all your subdomains, you like sort, unique them, do port scans on them, and then do web discovery. And then finally, you do like vulnerability scans, like nuclei. So this was basically it. But we were starting to lose faith in this process, and I was starting to like question like how valid it was, because no matter how you sort of shuffle these around and rearrange them, you're always going to miss something. Like during web discovery over here, you're going to visit websites, you're going to find links, and those links are going to have more subdomains. So you're going to find subdomains over here that aren't going to get port scanned. So are you going to loop back? Like, how many times do you loop back again? You know what I mean? So anyway, I was sort of losing faith in our tools and questioning everything, the meaning of life. So what was missing? Like, what was missing from this process was the question I was starting to ask. So I started to look for a better tool because the tools that we were using weren't finding what we needed to. So I tested out a whole bunch of them. I would find a tool, I would like read its README, I was like, this looks pretty cool, I'd run it, and then like there'd be some weird thing that would make me really suspicious, like some subtle issue with it, and then I would read the code, and I always regretted reading the code because like it just like destroyed my faith in it, and you know, I felt uncomfortable running it after that. So and I'm not hating on tools, but if you feel like I'm hating on your tool, you can throw the shmoo ball at me. I won't be offended. All right, so we tried these. We tried a mass, the harvester, recon for the win, which is just like a giant 3,000-line bash script. And none of them quite did what we wanted them to. But then I found Spiderfoot. So Spiderfoot surprised me. So it surprised me with its results, but especially with its code. So when I opened up Spiderfoot's code base, I was expecting to find something kind of like the other tools, where they had like this phased approach of like, you know, first you do subdomains, then you do port scanning. But that is not what I found with Spiderfoot. Spiderfoot does not work like this. So instead, Spiderfoot works recursively, where it has where each module basically intakes a type of data, does something to it, and then outputs a different type of data. So this is a simple example here where you have three modules, SSL, CERT, Nmap, and HTTP, where Nmap takes in a host and it outputs an open port. These other two modules, they take in an open port and they output a host. So it's sort of this loop that you can see where these modules work together. There's no start, there's no end. So let's like go through a scenario, right? So we input a host name, our target, evilcorp.com. It's a host, so it goes into Nmap. Nmap port scans it, finds open ports. Okay, these open ports get fed to SSL cert. SSL cert will pull down the cert, it'll parse it, it'll find other host names, right? HTTP will visit the website, it'll find links, it'll find more host names. So we end up with more host names, which go into Nmap, which become open ports, which again go into these other modules, which become more host names, which become open ports, which become more host names, which become more open ports, and so on and so on and so on and so on infinitely, right? Okay, so this is recursion. When I saw this in Spiderfoot's code base, I knew that it was the missing piece. It like clicked, and I was like, okay, that's what was missing. So I'm going to say the word recursion a lot during this talk, and you're probably going to be sick of it, but it's very important, okay? So this is a very important concept. Okay, Spiderfoot, it did something to me. It infected me, okay? It basically changed the way that I thought about scanning. It changed my core algorithm. Like, I know this kind of sounds crazy, and it was a little crazy because this was during the pandemic, and so during quarantine, I was just locked in my apartment, like getting super obsessed with Spiderfoot. But yeah, it made me realize that like this whole time, we've been doing OSINT wrong. And these other tools that we were using, they were just like toys by comparison to Spiderfoot. Spiderfoot wasn't perfect, okay? So has anyone here used Spiderfoot? Okay, a few of you. Okay, so have you experienced the issue where it just kind of like runs forever and never finishes? Yeah, that does tend to happen. So yeah, it was a little slow. It was missing a few features that we really needed, like a good DNS brute forcer, web screenshots, a good port scanner. But that was okay. Like I was like, okay, you know, we can just pull it the rest of the way over the finish line. We'll be good to go. So I knew it was the one. Okay, so I started by writing some modules. I wrote like a mass DNS module that had like some cool mutations where it would like have like customer-specific mutations that it would try, and it worked really well. I had an Nmap module, web screenshot, so I started to write these modules, started to integrate it with Neo4j. I was having a pretty good time. I was even able to speed up Spiderfoot by quite a bit. This is a tweet from Spiderfoot after we merged the change where basically it boosted the speed by a factor of almost 10, which was not bad. And basically, the final piece that we needed was we needed to make Spiderfoot multi-target. So Spiderfoot only supports a single domain, right, as a target. And the customers we were scanning, each one would have like 100 or more domains. So anyway, this was the last feature I wanted to implement. I was pretty excited about it. But then as soon as I started to actually do it, I realized it was going to be a lot of work, like extremely painful overhaul. And everything kind of fell apart. And not only that, there's this other thing called Spiderfoot HX, which really threw a wrench in the works because all these modules that I was writing weren't getting merged because they competed too much with the paid version of Spiderfoot. So basically I realized that I was either going to have to maintain my own fork of Spiderfoot, which I did not want to do because the code base is like 10 years old and it has some technical debt that I won't get into. But it was either that or write my own scanner. So these were my hopes and dreams about Spiderfoot. They kind of blew up and crashed and burned. But from my time in Spiderfoot, I learned a lot. This was actually really valuable experience because I learned how to write a recursive internet scanner, or at least how not to write a recursive internet scanner. I had an idea. So this was how Bbot was born, okay? And now we get to the fun part, all right? This is where the fun begins. How to write a recursive internet scanner. So my plan of attack for this new scanner was that I wanted to take the core idea of Spiderfoot. I wanted to take the recursion, and I wanted to build something for hackers. I wanted to build something that we could use on big assessments, and basically that was geared towards pen testers, bug bounty hunters, that kind of thing. And also, I kind of wanted to just write code without having to have it approved. So there's that too. So, step number one, building the core engine. So before I wrote any modules, I wanted to get the core engine working with recursive DNS resolution, just to see what that was like. It didn't take me too long to get this up and running, only a couple weeks. So this is a scan of Tesla.com. On the right, we have the terminal. On the left, we have the graph. Okay, so you can see this Bbot scan, and this is no port scanning, no subdomain enumeration, just DNS resolution, and it's only seeded with one domain, Tesla.com. So keep this in mind as we go forward, because this is what a normal Bbot scan looks like, and we may or may not be seeing some that are definitely not normal. Yeah, I was pretty excited. At this point, I was feeling very, I guess, invigorated. Like after being in Spiderfoot and sort of being weighed down by all of this like technical debt, it was like a very fresh feeling, kind of of like installing a new OS. When you install a new OS, everything's clean and wonderful. So yeah, but there were some things coming that I did not foresee, and I didn't quite realize what I was getting into with writing a recursive scanner. So what you're about to witness are a series of disasters that I encountered pretty quickly after first writing Bbot. So same deal here, terminal on the right, graph on the left. Just watch and see if you can figure out what the issue is here. See if you can figure out what happened. Just wait for it. Uh-oh. Yeah, something's happening there. So when I saw something like this, I'd always panic. So something is clearly going wrong here. This is not supposed to happen. And we could watch this, and it would keep going for some time. So what is happening here? Well, if we go and we look at it in Neo4j, so Bbot can output to multiple output sources. So Neo4j is a graph database where you can zoom in and see exactly what each data point is. So our target, which was this storeportal.levian.com, you can see that was our starting node. Then we have this giant amalgamation of all these things. So what was it that sort of triggered all of this? We just try, the interface is laggy because there's so many things in here. So if we could just try to find the center one, where did it all come from? We see that there's this storeportal.azurewebsites.net. Okay, so all right, so this basically means that in this case, what happened was it enumerated an entire cloud provider accidentally. So there's this recurring theme in early versions of Bbot where the scanner would step out of bounds, and basically 1 minute it'd be working totally fine, and I would go to get a cup of coffee, and then I'd come back and it'd find it had just gone completely off the rails, and I'd be frantically canceling it. The biggest culprits were cloud providers, which is what you saw. Basically, the client gives you a host name, and it happens to have a CNAME record that points to a cloud host name, and Bbot just assumes the entire cloud is in scope and just enumerates the entire provider. It's also DNS wildcards. Anyone who's done OSINT hates DNS wildcards with a burning passion, and I do too. That was if you were to encounter a wildcard domain, it would look pretty much the same as that explosion that we saw with the cloud provider. Same deal in the graph. Lots of false positives, really nasty. So let's continue on. This was a serious problem. I was not expecting to have to deal with these kinds of problems, but mostly these are sort of unique to recursive scanners. If you write a recursive scanner, you're going to have to deal with some problems that you would not have otherwise had to deal with. So disaster number 2, here we go. What's going on here? It could almost be like DNA replicating. Okay, but same deal here. This is going to run forever. It's never going to stop. And what exactly is happening? So again, we could go into Neo4j, and it would sort of reveal what exactly happened. So let's look at it. And we'll start off, it looks a little bit different in here. So we'll start off at the beginning with our target. In this case, I just scanned the local host. So we ended up with host name going to an open port, and then HTTPX visited the open port, and it found a URL. Okay, so we have our first URL. Pink nodes in this graph are URLs. So that URL was visited by HTTPX, and again produced another URL. And if you look closely, every single one of these URLs has a status code of 301, which is a redirect. So what this is it's an infinite redirect. Every time you hit the server, it redirects you to a brand new URL on the same server. This may seem contrived, like, oh, what a fun little demo with like a fun little graph to watch. No, no, no. We encountered this in the real world, and it was not fun to deal with. So this exists on the internet. Infinite HTTP redirect. If you visited that in a browser, you get like this redirected you too many times error message. So yeah, real thing, very painful to deal with. Okay, so starting to learn lessons here. The main lesson being that recursion is a harsh mistress, okay? The thing about recursion is that you always need an exit condition. Otherwise, it will just run forever. It'll go completely off the rails. So in the case of an internet scanner, that means that it could basically scan the entire internet if you're not careful. I'm not joking about that. Like basically, if you took off the restrictions on Bbot, it would crawl the entire internet. It would literally like resolve every DNS record. It would spider every website, like down to the deepest, darkest corner. So this concept of like restricting the recursive scanner into only scanning what you want is very important and very hard to pull off. So there were many times, I actually can't count how many times, we accidentally made a web spider. And this is like, this seems silly, but like when it comes to working in a recursive system, you only actually need 2 ingredients to make a web spider. The first one is you visit a URL, and then the second one is you extract other URLs from the response. If you have those 2 ingredients, you have a web spider. And we did that several times. Okay, final disaster. And this video isn't playing. Oh no. Give me just a second. Here we go. Okay. So this one's a little bit different. It's like a jellyfish, you know? He looks kind of cute. I don't know, just like swimming around. Okay, but don't be fooled. Don't be fooled. He's actually an unholy abomination. Okay, so if we look at this, in Neo4j, we can see what happened. And this is it. Okay, so you start off with a target, evilcorp.com, and we have some CNAME records. Okay, so we have pointing to a CNAME. Pointing to a CNAME, pointing to a CNAME, pointing to a CNAME. We have a chain of CNAMEs. But the chain of CNAMEs loops back around and ends up pointing right back. Chain of CNAMEs. But the chain of CNAMEs loops back around and ends up pointing right back at the original one. Is made up of user input. It's literally, it's user input all the way down. And you're ingesting it into your program. That's what you're doing when you're scanning the internet. So the way to think of it is, when you scan the internet, you're fuzzing your scanner, which means you need to be ready for the worst of the worst to happen, like random edge cases, weird misconfigurations, stuff that you wouldn't expect to see, but also malicious traps that are designed to DOS your scan. And the CNAME loop is a good example of this. Okay, so what's the solution, right? Well, don't trust anything you see on the internet. It's easy to say, but it's true, and it's never more true than when you're writing a recursive internet scanner. So you will never be able to write enough if statements to handle every edge case that you encounter, which means that you're going to have to attack them systematically, and that's what we had to do. So the solution that we came up with in Bbot was called scope distance. And basically, scope distance just assigned a number to every piece of data that just keeps track of how far it is from the main target. So basically, the further you get out, sort of the higher the scope distance is, and the more careful we need to be with that data. So this has 2 big advantages. The first one is it puts a hard cap on these explosive edge cases, where if you have like those infinite redirects, it basically will cut it off after a certain point. The other advantage is that it lets you venture safely out of bounds to do like explorative discovery. So this is important because you don't want to only look at stuff that's in scope. Sometimes you need to step out a little bit to enumerate sort of affiliates, that kind of thing. So here's a graphic showing like the concept of scope distance. So we have our target in green, evilcorp.com, scope distance of 0, meaning it's in scope. We have that resolving to an IP address, which is 1 hop away, so scope distance is 1. And then if we had that IP address reverse resolving to a third subdomain there, that would be scope distance is 2. So pretty straightforward. If the pointer resolved to an in-scope subdomain of evilcorp.com, it would go back to 0 and sort of reset. So in Bbot, you can tweak the DNS and HTTP distance separately. DNS by default is 2. It'll sort of like explore out to distance 2. HTTP is 0, meaning it'll only visit in-scope stuff. But if you turn it up, it'll do spidering and stuff like that. So, all right. So we're in the process of building this scanner. Our process is cyclical. It's basically we run a Bbot scan against some giant target. We see what broke and what went wrong. We fix it, and then we do it again. So this cycle continued, and Bbot kept getting better and better. So at first, almost every scan, it would do something horrible, and I'd have to like cancel it. But slowly, it started to behave better and better. And at this point, we had sort of like exercised most of the bigger demons. And Bbot, I would say it was about as functional as like the second Death Star, right? It wasn't finished, but like it was operational. Okay, so some solutions. We came up with solutions for the cloud providers. We were able to distinguish between cloud and non-cloud assets. Bbot, when you scan with it, will automatically tag each asset, whether it's in Google Cloud. It'll tell you whether it's in Azure or all this stuff. So we were able to treat cloud assets a little bit more delicately to make sure we weren't stepping out of bounds and into this giant cloud environment. And DNS wildcards, we fine-tuned our DNS wildcard detection to the point where, basically when it saw a wildcard, it would just kill it with fire and not let it do anything. This was a lot harder to get right than I thought it would be, but yeah, Bbot's DNS wildcard detection is very good. I'm very proud of that. So every day it would get more powerful, and I started to use subdomain enumeration as a way to like gauge our progress. So this graph here. This is from 2021. This is when Bbot was just starting to pass the other tools. So you can see these other tools like the Harvester, Subfinder, Amass. It was just starting to find more subdomains than these tools. And I was starting to get this feeling that Bbot was going to be like really powerful, like more than I sort of realized. But there were still problems to overcome. So we move on into the sort of second phase of development. So Bbot was operational, but I was basically at this point trying to make it as fast as possible. I kept adding threads to the program. Bbot is written in Python, by the way. So I was adding threads to try and just squeeze as much performance out of it as we could, because we were having to scan these huge targets, and it was sometimes a challenge to get the scan to finish in an amount of time that would leave us time to actually hack the things once we found them. So we had a week, right? So we had to like, if we could scan within the first day and have our scans done within the first day, that would be great. So I kept adding threads. Threading, I don't know how many of you have dealt with threads in programming, but they're slippery little buggers. So basically the threads would fight with each other, and I'd have to put them in locks to prevent them from accessing the same data at the same time, and then that would create deadlocks, and so I had to separate out the threads into separate pools, and it just became this horrible spaghetti mess of threads and locks. And I started to have flashbacks to my Spiderfoot days, because Spiderfoot's threading was very much like that. I then decided to do something that you should probably never do, which is just rip it all out and start over. I did not delete all of Bbot. but I deleted all of the threading stuff, and I completely overhauled it to use async I/O. So I absolutely love async I/O, and the amazing thing about it is that instead of having all of these concurrent threads, it's just everything runs in one thread, and it uses cooperations, cooperative multitasking. So it's more efficient, it's less bug prone, and I love it. I would not recommend, however, doing this. I would say if you're going to write a program, pick one, threading or async. I recommend async, and stick with it. But after the async, commit, basically I deleted like a whole bunch of that code, and it simplified Bbot a lot, and it made it faster. It was amazing. So feeling good again. Okay, so at this point, I had solved sort of the weird internet edge cases, solved the threading dilemma. We're good, right? We're good now. No, actually, there's still more. I guess, remember how I said that when you scan the internet, you're fuzzing your scanner. So this is true not just for your scanner, but when you scan the internet, you're also fuzzing all of the code libraries that your scanner depends on. In other words, like the libraries that it's built with. So it turns out that when it comes to Python, the async I/O part of Python is newer than the rest, meaning it's not as mature. So Python async I/O hasn't gotten nearly as much testing or fuzzing as the rest of Python. So yeah, when we overhauled Bbot to use async I/O, we fuzzed the absolute hell out of it, and we gave async I/O the fuzzing of its lifetime. Because the thing is when you run a Bbot scan on a large target, Bbot will easily make like 10 million DNS requests over the course of that scan. During that time, you're going to find all those weird edge cases. Maybe you handled them, but maybe your underlying code libraries still have difficulty with them. So here's a montage of all the issues that I opened with our underlying libraries. We found bugs in our DNS library. We found bugs in our HTTP library. We actually found bugs in Python. We actually found a bug in the Python programming language, which I was not expecting. But this was my life for a couple months after the async merge. Basically, I was having second thoughts about async, but I actually had a pretty good experience. Like the maintainers of these libraries were actually super responsive, and like these issues, like the vast majority of them were fixed after like a week. They were just like, oh yeah, I just need to do this one thing, and then it's fixed. So yeah, I had a really good experience there. Like the developers were very friendly, and it didn't take us long at all to get these fixed. The nice thing is, all of these code libraries have thousands of other projects that depend on them. So Bbot was like able to make those underlying libraries more stable. Yeah. So okay. So I know it's not normal for someone to admit to having this many bugs in their software, right? But I think it's important because it took me a long time to learn since I was self-taught, sort of like that this is a normal process and a normal part of deving. Like when you run into a bug, when you run into a strange bug with your underlying library, it's easy to get discouraged and give up. But this stuff is all fixable, and yeah, it's important to like keep going and keep trying. So yeah. Basically, that was one of the main lessons I learned. And if any of those bugs make you feel anxious or uncomfortable or unlikely to try Bbot, know that we have tests. So we have good code coverage. We have 92% code coverage. We're very proud of that. Every single one of those bugs that we encountered, we wrote a test for it to make sure it doesn't come back. And yeah, it's that cycle of testing and constant improvement that ends up creating stable software. So yeah, basically we feel very good about Bbot. Even though a recursive scanner is harder to build, it's also much more rewarding. So okay, so yeah, sort of in conclusion, I guess like the order of effort, or the level of effort was probably an order of magnitude higher than I expected it was going to be. But again, the rewards were also pretty good. So when I talk about sort of comparing bbot to other tools, I was continuing to run these subdomain enumerations, comparing it to these other tools. And just this week, I was able to basically run all those benchmarks again. And I picked ebay.com as a target for this because it's pretty big. ebay.com is one of the bigger domains. And I just wanted to see. So this is the final result of how many subdomains all of these tools were able to find. So you can see that, when it comes to that iceberg of like how many of those hidden subdomains did you uncover, bbot was able to uncover almost twice as many as these other tools. I should note, all of these tools actually ran pretty well, except for Amass ran for 24 hours. I had to cancel it after that. And unfortunately, Spiderfoot crashed my system after 20 minutes because it got stuck spidering ebay.com and ran out of memory. But yeah, so basically, if you're a bug bounty hunter and you're doing a bug bounty for ebay.com, just keep in mind the difference here, the difference between 5,100 subdomains and 3,500 subdomains. So that's almost 2,000 subdomains that you're missing that you would get with bbot, which potentially, those ones are less known and possibly not even looked at yet. So, okay, so my suffering is your gain. I made this for you. Basically, bbot is open source. It's super easy to install. You just pip install bbot. This is the GitHub here. So yeah, I hope you've enjoyed this talk. I hope that I've been able to convey the importance of recursion. And I know that as hackers, we get attached to our tools. We have our favorite tools. But I encourage you, if you're interested in OSINT, if you're a bug bounty hunter, if you're a hacker, and you use any of the other tools that we talked about in this talk, I encourage you to just take bbot for a spin and run it on those same targets and compare the output and see if it's able to find more subdomains. So yeah, I wanted to sort of just end the talk with a fun little demo, which is turning bbot into a Discord bot, because this is something we can all sort of appreciate. And it's important to note that bbot is a command line tool, but it's also a Python library. So when you pip install bbot, you can basically integrate it into your Python workflow, however you want to do that. And this example on the right here is just a little 50-line Discord bot that will essentially allow you to start bbot scans from within Discord. This is a fun little demo here. Okay, there you go. So you can see in this demo, we actually found a vulnerability. And that's something else about bbot is that my coworker who sits next to me in the office, Paul, he's a really good web hacker, and so he's written all of these crazy web modules for bbot that, in addition to all of the OSINT enumeration stuff, actually are able to find vulnerabilities that get you RCE. And we've got to the point where anytime we scan a big target, it's almost a guarantee that we get one of these one of these RCEs. So yeah, ending on that Discord bot, yeah, that's pretty much it. Any questions?
How many times did your ISP shut you down?
Okay, the question was how many times did our ISP shut us down? That's a good question. I'm thankful to say that feds never came knocking on our door. Yes, I was also pretty quick to cancel those scans when they stepped out of scope. However, we did get rate limited pretty hard. I had to, I worked pretty hard to basically make our DNS brute forcing work on these connections. But yes, so rate limiting was the biggest thing we ran into. Yeah. Anything else? All right, thanks everyone. We have stickers up here, so come get your bbot stickers if you want them. Yeah.
Hello, ShmooCon. Woo! Welcome to the last set of talks before we all head over into the main room. Should be pretty fun, actually. I think the after this wonderful talk, we're going to have Taskmaster next door, and so should be a pretty funny, or at least I think it'll be a pretty funny event. So definitely would encourage you to check out next door, and that'll happen right prior to closing. A few more announcements from me. First off, if you have any particular feedback for the conference, we're more than happy to accept that. You are the ones who make ShmooCon what it is. And so if you're seeing things, you have ideas, feel free to email them to us at info@shmoocon.org. If you're staying here at the Hilton, but you're not on the ShmooCon room block, if you would send actually your reservation number to info@shmoocon.org, it actually helps us out quite a bit. So we know that you're basically here staying for the conference. So if you didn't book through the room rate, but you're staying, we'd definitely appreciate it if you could shoot over your reservation number to info@shmoocon.org. Last thing from me is Ted is actually out here at one of the tables. And again, if you're looking to purchase a copy of the talks before they're posted in whatever time frame they get online, you can meet up with Ted there and get a copy that you can actually have much more quickly. So, without any further ado, I think this is going to be a pretty interesting talk, sharing some interesting insights into scaling things up to enterprise level security considerations. And so really, if you'd put your hands together, please welcome Eknath and Frank to the stage. Thank you.
Hello. Before we get started, I'd like to remind everybody that attack is cool, but defense is what pays the bills, and enterprise, of course. So because of that, we are really interested in monitoring threat activity and security misconfigurations in our enterprise environments. And every enterprise is unique in its own challenges and use cases. So you kind of end up needing a sort of a custom solution. In this session, we'll provide some insights into our journey of creating such a custom solution, and the problems that we faced and how we address them. More importantly, we're hoping that this serves as a sort of a blueprint, a set of design choices that we made in order to make the solution efficient, scalable, and something that works. And let me introduce us, the team behind the creation of this tool. This is Frank, who initiated this project and laid its foundations, essentially. I'm Eknath. I currently maintain and oversee improvements to this project. Our combined experiences from understanding the lay of the land to essentially refining the end product is what we are excited to share today. So going from first principles, we'll start with the requirements for such a security visibility tool. And I mean, what the essential expectations from this tool are, what the limitations we encountered from off-the-shelf tooling. Following that, Frank will go deeper into a case study of our custom solution. And then finally, we'll talk about the metrics, achievements, and close it up with the ROI. So let's start with understanding security visibility. In our specific case, we had 3 use cases. We had threat monitoring, we had compliance, and vulnerability management. In the threat case, you essentially need to know what processes are running where, what sort of activity is going on, like what sort of files are being created, where these connections are leading to. In the compliance context, it was mostly about capturing evidence, which means capturing configurations, stuff like how many root users exist, what the network interface card configurations are on every single host, stuff like that. In the vulnerability management context, it's mostly the SBOM related material, like what's the name of the package, what's the version of the package, and which host these are installed in. Now, because these hosts are the source of truth, it makes a lot of sense to collect the information directly from here instead of from the static configurations themselves. With that, we also had a couple of tenets to follow. It had to be efficient in the sense that it should not consume more resources than a particular threshold so that it does not interfere with the business applications themselves. It should be, sorry. Oh yeah. It should be very reliable because it is the single source of truth for all of this information. So if it were to break, then vulnerability management, threat monitoring, and compliance would break, so we can't have that happen. And then it should be able to monitor a large fleet. By large, in our context at least, we mean a little over 100,000 hosts. And then we have fairly custom infrastructure, and this solution needs to integrate well with it so that the ops and the DevOps folks, they don't have to do extra work in order to maintain and run this tool. And lastly, we need the data to be accessed and analyzed by a variety of teams. So the solution has to be fairly open and follow standard protocols. All right, so coming to the sort of high-level limitations of off-the-shelf standard tooling, it's one that we realized that it was getting quite expensive at scale. And I think the at-scale part is quite important to highlight here, because if the scale is not too high, then I think off-the-shelf tools, especially from a cost perspective, make a lot of sense. Secondly, like I said in the previous slide, that our infrastructure handling is quite custom. So it was getting hard to integrate and operate into this environment. Then the data gets, because off-the-shelf tooling is meant for literally everybody, they cannot propose how the data should be accessed. So they provide typically a unified UI solution, which makes exporting and programmatic access of this data sort of hard, a second-class citizen, if you will. So that is a problem. And then from the data collection standpoint, there are two more problems that we encountered, which is the ability to customize and the ability to optimize. For example, we have servers that we don't really care for how often a certain process has run, or if the processor has run thousands of times or creating thousands of DNS requests, things like that. We'd like to deduplicate this data. So modifying all these sort of minutia we found that it was quite hard in the off-the-shelf solutions. I would like to talk about the opposite of this, meaning building your own solution. Second point onwards, everything else is exactly the inverse. But the first point, the expensive at scale part, specifically the licensing bit is gone, but it is replaced with engineering time though. So to each his own. And with that, I'll hand over the stage to Frank to talk about the case study.
So I'm going to talk about the technical aspects of what makes a visibility solution, and I'm going to use our own as an example. Ours is called Bigfoot, as you see. So pretty much all visibility solutions would have at least three main components. Try to do this in the diagram here on the left. We have the data acquisition, so that's just typically an agent that gets the data from a host or a node or whatever. Then in the middle, we have a layer where we receive the data and aggregate it. And then, of course, we have the storage as well, just to make it usable in a way. Now, in our case, the storage is actually where it differs quite a bit from a vendor solution. Ours is meant to be open, so accessible by many different tools. I have put a few examples on there, but this is not limited to those. So we want to gather the data. We want to make it accessible to standard tools. We don't even have a UI like many other commercial tools. I'm going to dive into each of those three layers, like on a technical level, much deeper, starting with the data acquisition on the left. But before I can talk about the agent itself, I have to talk a little bit about eBPF, because it's a critical component of the solution. So eBPF is a Linux feature that allows loading of probes, they're called probes, little programs, functions, into the kernel at runtime by a user space program. So you can load a tiny little bit of code into the kernel. It gets attached to a function, a syscall, a trace point, or anywhere in the kernel, really. And whenever the kernel hits that function or trace point, it will execute that probe, that little bit of code. Now, you may be thinking that injecting code into the kernel at runtime sounds kind of dangerous, but this is not a kernel module, so it's not meant to be able to crash the kernel in any way. So it's perfectly safe, or it's supposed to be perfectly safe. There's a little caveat at the bottom. Now, to give you an idea what BPF usually, people say that BPF to the kernel is like JavaScript to a browser. That's largely correct, but it's not 100% true, but it gets the point across, I think. Now, why are we using BPF? We use BPF to capture events from the kernel. So when I say events, I mean a process opened, a DNS lookup was made, a file was accessed. These are, when I say events, that's what I mean. And BPF is reliable, and it is also the most efficient way to get data out of a kernel, at this point anyway. Now let's briefly look at what's necessary to get BPF code into the kernel here. So we start off with a little bit of C code that typically is C. It doesn't have to be, but it often is. When I say C, it is syntactically C, but there are a lot of restrictions on BPF code, so let's call it restricted C, I think, at this point. This C code is then compiled into BPF bytecode with the standard tooling LLVM. Should highlight here that if you had used BPF in the past, you may have had to install like compilers and the tool chain onto target hosts, but that's no longer the case. We can do this during a build now. There's no need to deploy a compiler and the kernel headers to all the targets anymore. So this can happen at build time with modern kernels anyway. Now, once we have the BPF bytecode, then we need to load it into kernel. This could be done with low-level syscalls, but using a library is way more convenient, of course, for this. So we use the Cilium library because our agent is written in Go. That works quite well. Now, the library would then take the BPF bytecode, send it to the kernel to be loaded. At this point, this is where the kernel then applies some checks. It will run it through a verifier to ensure that the code is actually safe. So it will look for things like unbounded loops, unsafe memory access, and reject any probe that uses that. So once the BPF probe is found to be safe, it then gets loaded into kernel and attached to whatever point in the kernel itself. So, and once it's attached, then it will of course be executed as that code that it's attached to gets run by the kernel. BPF probes are usually stateless, but they do have, there are BPF data structures called maps that can be used to maintain state or to send data into user space, which we are going to, of course, use quite heavily, actually. BPF is quite a large topic, and I'm just scratching the surface here. I don't want to go into too much detail, so I left some resources there if you're interested. Now, let's look at how we use BPF in the agent. So our agent has two methods of getting data from a host. The first one is obviously eBPF. As I just said, it would inject a probe into the kernel. The probe would run when an event happens, and it would exfil data out of kernel space into user space. And the second method is a much easier way that doesn't involve the kernel, like not directly anyway. That's just, we call it scheduled jobs. Those are just functions to read configuration of a host. Configuration could be things like the user accounts that are set up on the host, configuration of NTP, all the packages that are installed, that sort of thing. This data collected in either way will then be enriched. And there's a pipeline, it gets enriched and gets converted into protobuf, and then it gets sent off the host to the central place. In this case, we use gRPC. Why we use gRPC, I will talk about later. Since we talk about implementation here, I just want to mention that this agent is written in Go. It gives us a reasonably low-level access to everything. It has excellent library support for BPF libraries and JPC, protobuf, all of this is well supported. The concurrency is very simple, so that's great for performance. And last but not least is Go binaries are just standalone single files. That's a great feature to have in a visibility solution at scale, because it makes the deployment so much easier. Having just a single file to roll out into a very large fleet, it helps. Nobody wants to manage Python dependencies on thousands of hosts. So Go fits quite well for us. I mentioned enrichment here just briefly. I'm going to dive into that a little bit more, into the pipeline here. Enrichment means adding context or metadata, process metadata specifically, to events that happen in the kernel. So let's say there's a DNS event that happened on a host. It's not usually enough to know that it happened on a specific host. You need to know where it came from. Specifically, which process made that DNS query. And even further, we want to know which process made that process that made the DNS query. So the whole ancestry is useful as well, up to and including PIT1 if possible. So I have put a little bit of an example here of a DNS event on the diagram here. I'm going to walk through it, through the full pipeline real briefly. As on the left, the white box that represents the UDP send function inside the kernel. And I tried to put a BPF probe on top, so that should signify that there's a BPF probe attached to it, meaning whenever the kernel calls a UDP send function, the BPF probe runs first. So that would, of course, be called for a DNS query. The BPF probe would then walk the kernel structures. It would extract the timestamp, the PID of the process that did it, and the raw packet, as it is on the wire, the raw DNS packet. This data would then be sent to user space via a ring buffer. This is a type of BPF map that allows sending from kernel space into user space. It also preserves ordering, which is quite nice. So at this point, we have raw data in user space, basically. The kernel carries on doing its thing. It's no longer involved. But we have this raw data. Now we need to do something with it. The first thing that happens is enrichment, meaning we attach process information about this event, meaning the process that did it plus all the ancestors to it. All of this will be, you can see it there in the middle in the white box. So now we have still raw DNS data, but we know where it came from. At this point, the ordering doesn't matter anymore. We can now process this thing in parallel any further, and we enrich, not enriched. At this point, we parse the DNS packet, convert timestamps, and now we have a complete event. At this point, it's a complete event. It gets turned into protobuf and, again, shipped off the host. Now, in case you're wondering where the metadata for this process enrichment comes from, that too is captured with BPF. So we're tracking in memory, tracking process creation, exits, and forks. So that's how we maintain the representation of the process state in memory, allowing for fast enrichment. So I have to briefly talk about filtering. Since efficiency is one of our main goals, we have to keep the amount of noise in the system to a manageable level, really. Depending on workloads, and some services are quite heavy in that regard. So when you think about attaching a BPF probe into the kernel and that running constantly, it can create a lot of noise. So we want to filter. Where do we filter? Preferably, we want to filter as early as possible, and that means in the BPF probe. And we do this. Now, unfortunately, not everything can be filtered in BPF, because BPF is very limiting in what you can do in it. So evaluating a regex isn't an option. There's other things that don't quite work there. So it's very difficult to do. But things like muting a process, that could be done in BPF. It would prevent the event from even being emitted to user space, which is nice. There's no further processing, the kernel just carries on. Now, if we can't do this, then we can at least apply more complex rules, like as I said, regexes and so on, further in the pipeline during processing once the packet, in this case, is parsed. So we can drop it. And the last bit where we want to reduce noise is via dedupe. Imagine a DNS query being made multiple times per second. There's no real value in knowing that the same process made the same query hundreds of times. So we dedupe as well before shipping off the host into the agent, into the collector, the next stage. So there's 3 layers of filtering, and that's quite important to just keep things under control. Now, I mentioned BPF sort of in abstract terms so far. I want to show you an example. Cool. So this is an example of what a BPF probe in C code looks like. So you can see, well, it's standard, as a standard function, looks like it. There's a few things I want to highlight here. At the top, you see the type of probe it is and where it is attached in the kernel. So this one is going to be called every time a process forks on the system. So once the probe runs, it will, in this case, read the PID from the current process, from the child process and the parent process. Then it will build a structure and on the ring buffer and ship it into user space, and that's it. And then the probe returns, and the kernel just carries on as normal. And the user space then processes this data. So this is really a very minimal overhead onto the kernel. It only adds a few instructions to it. It's hardly noticeable, even with performance tooling. And we don't want to impact the host, of course, so we have to be fast. One thing to note here is that BPF is very modular, so it all looks like this. It's just a function, typically, without complex dependencies like you would normally see in standard C code, which helps with maintainability, of course. Now, to be complete, I want to show you the other second method I mentioned of getting data off the host is reading from the OS. We call them scheduled jobs. These are really just nothing special. They're just functions, Go functions that are called on an interval. So in this case, when it runs, basically it will collect whatever data it needs. So this one reads the proc modules, then turns it in a protobuf, and again ships it off the host for aggregation. Dedupling happens here too, because when you run something on a schedule, like the packages installed on a host don't change very often. So if you run it like every hour, there's no need to send a record every hour if it hasn't changed. Now, we're moving off the host now, so the data acquisition is done. Now we come to the aggregation layer. We call this the collector. Basically, this is the middle part of the 3 layers, and let's zoom into this. Now, this is the thing that processes all the records shipped off the hosts by agents. It's sort of a central component. So fundamentally, its job is to receive a stream of records, events, or otherwise, from a large number of agents in the fleet. Then it demultiplexes them by record type, and then it stores them, of course. So if you can read this, yeah. So on the right, the table A and table B, this just could be a DNS, all the DNS records. It could be all the process records or packages and so on. So I haven't talked about the mechanism yet that we use to ship records from an agent to the collector. It's quite important because it goes over the network. So we've chosen gRPC and protobuf here between agent and collector because gRPC uses HTTP2, so it only opens a single connection, which is nice. It's extremely well supported in Go, so we get authentication, retry, everything out of the box. And protobufs can be packed very efficiently. It's a binary format. Now, could we have done this with a standard JSON API over HTTP? Yes, absolutely. but it's a lot less efficient at that point because you're shipping JSON, which has a lot of overhead. And also you would have to maintain like connections, there's error handling and all of these things. We get this out of the box for free with gRPC, so no need to do this manually. Now, another thing I want to highlight here is that while the collector receives protobufs over the network from agents, it produces as output Parquet files. Why Parquet files? I will talk in the next slide a little bit. Now, the thing is with Parquet is that you need a schema to write it. It's structured format, so you need a schema. Now, we have a protobuf, we have a Parquet schema, and do we want to maintain two schemas? Not really. So the best way to do it, to handle this situation is really to generate the Parquet schema on the fly. That's what we did. Whenever the collector receives a protobuf of any kind, it will just generate the Parquet schema that matches it on the fly and write the files that way. That keeps the maintenance overhead to a minimum because we don't have to maintain two schemas. We don't have to touch the collector at all if we add a new record or something like that. So just adding a new event to the agent would be trivial because you just add it as a protobuf, send it to the collector, and the collector knows immediately what to do with it, even if it hasn't been changed. Now, one thing I'd like to highlight here is that the collector, the central component, is stateless. That is possible because all the records that are emitted by the agents are fully denormalized, so they're fully self-contained, and there's no need to correlate with other records or anything else, like add any further processing, no further enrichment. This data can just be stored as is, as it comes in from protobuf. Many other solutions perform processing at this stage. Now, what do we get for keeping it stateless? Simplicity, like most of all. That's one of the goals, after all. And it improves reliability, of course, as well. It's extremely fast, and we have some numbers for you later. And it allows us to scale to any size, really. We're just adding more hosts, and it just scales that way. If it wasn't stateless, like if we did additional processing, things would get really complex at this stage because you would have to build a Hadoop cluster and run Kafka and Spark, perhaps, and things get out of hand really quickly. Much higher maintenance. So doing all the enrichment inside the agent really keeps the processing to a minimum and it's really simple. Now, let's move on to the last of the three layers. That's the storage. So I mentioned Parquet. Why do we use Parquet? Well, it's column-oriented. It's very fast to use, very fast to access by different tools. It's very efficient and has a lot of compression and encoding schemes. So it reduces the volume quite a bit, which we need. And most importantly, though, it is well supported by all the big data tools out there. So pretty much anything can read Parquet files. So that was one of our requirements. We want to be able to use this data in many different ways, like real-time monitoring, retrospective, like we want to export it somewhere. So we want to have access to the data. So the data that comes in from the aggregator is really just a stream of Parquet files. It's grouped by, partitioned by type and day. I think there's an example prefix in the slide. Yep, if you can read it. Now, as I said before, this is also where we differ quite a bit from commercial solutions, where there's a dedicated UI, and the data is often hidden behind it. No, this doesn't even have a UI, so it's bring your own, basically. Just there's all the data. It's in a format that's very compatible, and you can analyze it with a number of different tools. Now, we talked about the agent, so the collection, the agent, collector, and storage. Now, I want to show you what an example record looks like, what an actual event collected from a host looks like. Now, I cut off a lot of information here to make it fit. So this is incomplete, but it should be enough. So there's really three main parts to it. This is just formatted as JSON, so I can read it more easily. So there's information about the asset at the top. So it would typically be a host name and some sort of asset identifier, wherever this came from, this event. The second is the enriched process list. This is basically saying that this is the parent process, and then there's the grandparent process, and then all the way to PID 1. This list is actually, if you walk the PIDs, it's truncated, so it won't fit. And the last bit at the bottom, this is where all the event-specific fields or the event-specific data lives. In this case, this is a process event, so a process was opened. So it would have things like the command line that was used, the environment variables, the user, and so on, and current working directory. And with this, I hand it back to Ignath to talk about metrics and benefits.
All right. So just as a reminder, our objective was to create an efficient, reliable, cheap to operate solution which covers a lot of customization, optimization that we really like to do. And this solution has been running for over a year at Stripe in production now. It covers over 100,000 nodes at any given time of the day. In terms of an achievement, I'd say it's pretty cool that a vast majority of the nodes consume less than 1% of the CPU. And the total number of records produced a second is around 180,000. Of course, there are spiky situations and whatnot. This is just the average I'm talking about. And thanks to the simplicity of the design of the collector, all of the collection only requires active 64 vCPUs. So in a typical AWS machine, that would be just 4 boxes, although we have provision for spikes and the likes of that. But this is what is actively being used. And cumulatively, again, even though the number of records is 180,000, and you saw that the enriched process metadata with the JSON blob is pretty large, we use Parquet, and that results in a pretty significant drop in the overall sizes. It results in around 8 terabytes a day. So these are just some numbers, but I'd like to highlight a very practical advantage of creating such a tool. People who have worked in enterprises and have worked on security migrations have this very real practical experience. Now, AWS very actively discourages usage of IMDS v1. But the question is, how do you go about finding who's using it and what you can do about it? One option is to grep your static code. The problem is you have third-party binaries, you have dependencies, you have dynamic path generation. There's no way to reliably find out who all is using grep. The other is to get real hard about it, deploy sysdig, and it'll give you the right answer. But unfortunately, it's a local tool. You have to deploy it at scale, collect all this data at scale, analyze all this data at scale. Super painful. Third option is YOLO, test in production. Just disable IMDS v1, find out who breaks, and then watch who complains, and that. The other option is to use AWS metrics. Now, the problem with AWS metrics is while they are accurate, in at least our context, on a typical EC2 host, we have processes, binaries that are owned by different product teams, different service teams, which means AWS is only going to give you host level information. It's not going to give you which process is accessing IMDS v1, which means attribution becomes hard to which team do you have to go and say, all right, database team, you got to change it to IMDS v2 and stuff like that. So that is a problem as well. As you might have guessed, our solution, we just had to add a eBPF probe that monitors traffic on the local link address and convert it into a protobuf, just a bunch of strings, and ship it off to the collector. The volume was very low, as you can imagine, compared to something like a socket event or file event. And the best part, an additional advantage of doing something like this is that it very naturally integrated with our data tooling. So you could draw graphs, you could see that, over time, how the usage is reducing. It was just a real win-win sort of an outcome of this. Yeah, with that, I'd like to talk a little bit more about the investment, because earlier when we were talking about what it takes to build a custom solution, one of the things was to talk about the licensing cost, the expensive at scale. In our specific situation, getting to POC took about 3 months, one person, that was Frank. And in about 6 months, we got it deployed on production. And currently, I actively maintain it and make improvements. So that was sort of the investment. But I'd like to highlight another important thing here. It is this, that thanks to our operating system and infrastructure teams, at Stripe, we run only a handful of OS versions and a handful of kernel versions. Had it been a lot more, and had it been like wild, we'd have to do a lot more testing, a lot more reliability exercises, efficiency exercises to be sure that our thresholds are met and not breached, which makes a humongous difference in the development time, the quality of the solution. So, which is why I think which was an important contributor in this case. The other thing is that, as you saw, almost all of the solution is built on extremely stable modern technology like eBPF, protobufs, gRPC, Parquet. I think really leveraging these very standard and stable solutions has helped out in our situation here. So the return on investment. This is all on the basis of running this in production for the past year. We had one minor incident in a very small set of hosts. There was a kernel bug, and it led to some crashes, but that's just been this one situation. Compared to the evaluations that we had done against standard tooling, all these OS query-based tools, it requires a lot less CPU, a lot less memory. Memory specifically because of the usage of the ring buffer, which bounds the number of elements that can be in memory, so nothing can overwhelm it, and a lot of such design optimizations. Currently, it drives a large part of the compliance requirements. Almost all of the vulnerability management relies on this being the source of truth for the entire org. And as you saw in terms of flexibility and customization about the IMDSV one, you can add arbitrary events. You can answer operational shaped questions. Yeah, that has been a real win for us. And lastly, at Stripe, because we're a payment processing company, you can imagine, we have cardholder data, we have all these very sensitive payment processing environments, and it's pretty awesome that we're able to 100% trust the code. I mean, really, trust me and him, but I think that is a real win here too, that you don't have to trust third party, there are no risks of supply chain attacks, that sort of stuff. So in conclusion, I'd like to say that our experience has been that getting visibility, security visibility into your fleet is not that hard. We did, and I hope that so can you. Questions? Oh.
When you first developed this, was this kind of like your first project using eBPF, or had you had previous experience with that?
The question was this our first encounter with eBPF, besides some very basic Python testing? Absolutely. Yeah, this was the first. Yep.
So for your communication paths between your data from your collector to your storage, or even from your agent to your collector, did you ever think about using things like OpenTelemetry instead of just going with gRPC and protobufs? Because OpenTelemetry does support gRPC and protobufs, for example.
Do you want to answer that?
I haven't really considered it.
You said you have or you have not?
No, I have not. No. And to be honest, open telemetry is a bit of a sore point in our monorepo. So I don't know if anyone has had some experience with that.
Why so?
No, the constantly breaking dependencies. So open telemetry it has a very bad rep in Stripe at the moment. As a repo, like the dependencies were not managed properly and it constantly broke it.
Okay, thanks.
So, but yeah, we have not considered using that. So we wanted to be the most flexible, and that really means like protobufs for ourselves. Yeah, and we can adjust to what we need.
And I think another point here is also that OpenTelemetry would be one more layer on top of the native tooling, right? Like you have gRPC and all is natively supported. You have the OpenTelemetry would be another level of import. We didn't really see the need for that. Yep.
Yep. So you mentioned earlier in the presentation where you talk about applying filters to eBPF like at the beginning. How do you, field that from, I guess, your monitoring teams and decide which filters go in? And then how do you apply them throughout your fleet?
I don't quite understand.
So you have like your eBPF filters in the beginning where you want to like exclude processes and things like that. What is your internal process for validating whether something should be excluded or not? And then how do you distribute those changes out to the fleet?
Right. So the first level of this would be to deploy it on a small set of hosts, collect data, and see what is noisy. Because our objective is not to actively discard data, it's to reduce noise. Right? So first step is to identify the noise. And once we have sufficient selection of that, we, as Frank mentioned, we had a deduplication layer as well to keep the unique data, but not discard everything. The last step would be to talk to those guys. That's the threat detection team. Can you wave? Yeah, so they are the subject matter experts on what can and cannot be discarded. That's essentially the loop.
Extensibility part, say like public security indicators in your org, do they need to make their own eBPF filters for hooks or otherwise, or is there a framework that you built that translate down?
So the question was, how do other developers extend this Bigfoot? So at Stripe, we have a monorepo, so people can just open PRs. That's not a problem. But in terms of practice, we work very closely with the people who have. And in fact, the IMDS was created by someone outside of us. We are definitely the reviewers, though. Yes? So we basically keep a hash of the event, and we maintain a counter of how many times it has occurred, whatever is unique, because obviously adding timestamp would make it non-unique. So we keep the relevant bits in memory, and like depending on what sort of event it is, we allow 100 duplicate events an hour, because even the number of events is a relevant bit, right? Like a DDoS sort of a situation. So we certainly keep track of that. But depending on the event, it's a time-based and a counter-based limit. Yes?
To what extent can this tooling and infrastructure be used for like profiling and like performance measurement use cases?
So I think eBPF is obviously very commonly used for profiling and performance, but that also goes into the depths of a lot. As you can see, like our probes are very specific to processes. We don't monitor what the process is doing in terms of memory allocations and CPU usage or performance counters or any such thing. So, and this is meant for scale, right? And typically these profiling tools are like very specific to a specific use case. So while the eBPF might be the commonality there, I don't think this is directly applicable in that. Nothing stopping you from, but I don't think it would work out very naturally in that. Because you want iterative development and all of that there, right? Like you find the first bottleneck, then you go into the next one. And yes?
This fleet itself was mainly Linux servers, like running Kubernetes workloads or whatsoever.
It's native EC2 hosts. In fact, it's physical boxes, it's micro VMs, and container-based environments as well. Yeah, yeah, yeah. Actually, exclusively Linux. Yes?
Do you use anything special to learn eBPF or just trial and error?
Just the resources that were listed in the thing, in the slides. Oh, sorry, yes. The question was, what resources did we use for learning eBPF? And that was primarily just the resources that were mentioned in the slides.
Lots of Googling.
Drinks. Okay, thank you.